Swayam Prabha. Digital India. Educated India.
Good morning. Welcome you all for this next lecture in this particular course on analytical, spectral and microscopy applications of inorganic compounds and nanomaterials. We have been looking at in the past 7-8 classes or so various techniques related to the analytical methods like atomic absorption and thermal methods. We have looked at all of these. Let us look at another method for this class. Probably one more class is something on the electrochemical or electroanalytical kind of methods. So obviously the title says this electrochemical and electroanalytical. So what is there in the electrochemical? So you have a voltage and you have a, so therefore these are dependent on voltage and current. So this is the main aspect that you are going to look at. There are other things are also there. You would use something like an electrode. Obviously without that you can't get electrode, and then you would use a medium. So all of these and the way you measure, those are the parameters that it can happen. So in this electrochemical or electroanalytical, one and the same, what we are going to study is you will look at either the voltage, current, by varying these parameters, either of those, keep one of them constant, change the other one. You can also work at different electrodes, you can work in different medium. All these kinds of things will come as a function of these electrochemical, electroanalytical techniques. So that's very simple. I'm sure you know from your 12th standard, even early stage itself, is that the galvanic cell, this particular equation, this cell configuration is very familiar to everyone in chemical sciences. Zinc sulfate, copper sulfate for copper, and clearly know for the galvanic cell you have the two compartments, compartment 1 with one of the electrode which is the anode here, and compartment 2 with another electrode which is the cathode, and these two are connected by two things. One is the two electrodes are connected obviously with this electrical circuit, and which you call it as a voltmeter, and these two solutions have to also be connected, that's by the salt bridge kind of thing. So a lot of experiments can be carried out, we will look into those. So the potentiometry is the one of them. So you measure the difference in the potential between the the reference or standard versus this. And in the coulometry, you are going to measure the current as a function of time, how much of the current is consumed, etc., etc. The voltammetry, what you do is you apply a particular potential and start measuring the current, and you keep scanning the potential and then measure the current. So using these, you can have a variety of techniques. So this is not necessary to remember entire thing, but what I would say is there's some just to get an idea. So when you talk about any of these the techniques in the static mode, that means no stirring, dynamic mode, there is a stirring in solution, and that's what basically it means. Don't take any other kinds of a meaning for this. This can be static, the potentiometry, so you measure the potential. You can have a dynamic where you are looking at the controlled potential or controlled current. These are possible. So in the controlled current, you measure the current versus the time, and in the controlled potential you can have other techniques. So you can keep a potential is controlled but can be swept. So a value, another value as a function of time or a function of whatever the profile of the potential wave that you can change. So in this you can have amperometry, which is the measuring the current, and controlled potential, the current versus the time. Now in the variable potential, where you have a potential keep changing from one value to the other slowly as a function of time, and in that you can have a solution which is at in a vigorously stirred condition, and there is another one you have a no disturbance, no stirring. So that is what is called quiescent, which means silent. So there is no disturbance in that solution at all. So using these techniques you can make the stirred hydrodynamic voltammetry or stripping voltammetry. In the non stirred conditions you can get the polarography, pulse potential, cyclic voltammetry kind of things. And this is what we are going to look at in this entire part of this electroanalytical one. The other things are somewhat very simpler, so I am not bringing into this particular lectures of this plus the next one at all. I hope you understand. You don't need to remember every aspect of this. All that you need to know is the techniques are under the stirring and without stirring kind, and they can be with the controlled potential, with a controlled current. Under the controlled potential you can have a variable, you can have a fixed. Under the variable you have a solution being stirred, solution not being stirred, and these can give the techniques of this. Polarography is a very old technique. Pulse polarography is a part of that one, where with the pulses of the potential which is being measured, and the most recent technique is the cyclic voltammetry, which is used for characterizing things, for the analytical characterization, quantifications, identification. So you can do all of these things. So we're using the cyclic voltammetry. You can use identification. So because there is a potential, etc., and quantification. And if you have a mixture, also you can study even from mixtures as well. So they're like any other analytical method that we studied earlier, where you can easily do those the separating the things of the peaks, individual peaks of that. Okay, so exactly the same kind of thing in analytical will be a good technique if you can identify, you can quantify, if you can also resolve from a mixture, if you have a mixture that is being used in that. So such kind of techniques we saw even in the thermal techniques as well. So already mentioned to you in the potentiometry, what you are measuring is the potential of that particular solution that you have, in which you put your electrode, and therefore there is a equilibrium occurring between the solution and the electrode, because any electron transferred from the electrode to the species, from the species to the electrode, does happen at the interface. So therefore that is where you are looking at the equilibrium. Once you have an equilibrium is being established between the solution and the interface or the electrode surface, then what the potential will convey? The potential will convey to you is proportional to the kind of a species, kind of a reaction, or relevant to the kind of a reaction that is happening, or amount of the species also. In fact, I am sure you must have done in your BSc first year something like potentiometric titrations. So potentiometric titrations, I am sure there are various measurements, various types of things where you measure the potential. Of course, it can be an acid base, it can be redox, or it can be complexometric. So variety of these things. So in all these things you have some solution, you are titrating with something, that is why titrometry, and when you titrate something, something is consumed, and therefore you have something else remaining, so you keep measuring that. So therefore the potentials keep changing as a function of variation. There can be many other kinds of reactions. I am sure all these three kinds of reactions are done in the BSc first year, second year for the electrochemical, in the physical chemistry experiments. So that's potentiometric titrations where you have. Okay, coulometry you can have where you pass the current completely to transform species from one oxidation state to another, or from one oxidized form to a neutral form, something like copper 2 plus going to copper 0, etc. So any of these, in some cases n plus, mn plus going to mn minus 1 plus, that means 1 electron thing. Of course you can have 2 electrons also potential. So you can keep the potential static calorimetry, controlled potential calorimetry, all these names come for the same. So, you are essentially doing a bulk electrolysis of the material that is present in that particular cell. Now, if you count the number of electrons or if you measure the current, one and the equal. So, when you say the number of electrons or the measuring the current, then once you measure the current, obviously you are able to convert that current into the species or concentration, kind of thing. Okay, the third technique, which is the voltammetry part of it. So, you vary the potential, okay, and then you measure the current. So, you can do that in a linear way, it is called linear voltammetry. You can do it in a cyclic way, it is called cyclic voltammetry. So, what you do, you start at a particular potential, keep sweep towards one direction, and then at some stage you switch back your direction of the potential sweep, and then you return back to the normal, and that will be a cyclic kind of a thing. Again, this method can give you identification, quantification, all those kinds of parameters can be obtained. So, therefore, it is a very powerful technique, and then we will be looking at. Other thing is that you will be using something like millimolar concentration of solution. So, therefore, it is not a destructive kind of a thing. You require less concentration, it is not a non-destructive, because very small part of that species will undergo reaction at the electrode surface, and the bulk nothing happens. That means you can use that compound again, but unfortunately you will use large excess of electrolyte, bulk electrolyte. So, for what reason, etc., we will be seeing just in a while. For the time being, let us take that. So, if you can separate this, you can get back your species, but since you are using very small concentration, you do not need to look for the separating that one, and also you do not require a huge electrodes, etc. You can have a very small micro kind of electrodes are good enough for doing that too. So, what we are talking about in all these things, we are talking about the electron transfer. Electron transfer can occur in the medium, in the solution phase, which you refer in terms of the homogeneous, and between the solution and the solid, which you can call it as the heterogeneous. So, electron transfer within the same state. So, for example, you have the reductant, you have the oxidant, both are in solution, let us say. So, then you can expect that as a homogeneous. For example, here is a ferrocenium ion is there, and in the positive cation, and the Cp star twice complex of a cobalt. So, the cobalt 2 complex. So, what will happen? This will give an electron, the cobalt complex will give an electron to the ferrocenium, both are in solution. That is why it is referred as the homogeneous electron transfer. And then what will happen? The ferrocenium ion will become ferrocene because it received one electron. So, it is basically a reduced form. Fc is a reduced form of the Fc plus, and now the Cp cobalt Cp star 2 becomes cobalt Cp star twice plus, and that means oxidized. So, the cobalt complex oxidized and the iron complex got reduced. Okay, but in both of these things, it is the reaction happening between the reductant and oxidant simultaneously in the solution phase itself, within the same state, within the same phase. So, that is what you have the homogeneous. But on the other hand, if you look at this example, you have an electrode and you have a solution surrounding the electrode. Suppose you have this is your electrode and this is your solution. So, therefore, your species will interact at the electrode surface. So, that is what is heterogeneous, because the species is coming from solution and the electrochemical or electron transfer is occurring at the surface, which is at the solid surface. So, therefore, that is what is called the heterogeneous. So, this will be heterogeneous electron transfer. So, you will have a homogeneous, heterogeneous. You can see that the ferrocenium ion, which is in solution, electrode obviously solid, and therefore, there is electron transfer occurring. So, from electrode to the ferrocenium, ferrocenium becomes ferrocene, the of course electrode will give the electron, so therefore, and then circuit will be finished, so that we don't need to look at that. So you have essentially a homogeneous type and the heterogeneous type, and all the reactions that we are studying in the electrochemistry are heterogeneous type, because they are from solution to the solid, the electrode surface. We won't say solid, but we will say electrode surface kind of a thing. Okay, so as I said that mainly we are going to focus on cyclic voltammetry in the entire thing. So therefore, let us look at the cell configuration experiment, etc. There are 3 electrodes, not the 2 in the earlier case, potentiometry, etc. You need just only 1 electrode there, because you are using a solution, then you connect it and then find the difference in the potential. Here you require 3 electrode, which is the working electrode that you have here, and you have a reference electrode, and then you have a counter electrode. Hold on for a minute, I'll be explaining all of those things. And then you have your solution, and sometimes you want to pass some nitrogen gas, other kinds of things, etc., for inert, for reaction purposes, etc., so that you have some other facility to connect with that. And these electrodes are connected to the circuit. Okay, we don't need to know the circuit part of it. So cyclic voltammetry, as I mentioned a few moments ago, that you sweep the potential and measure the current, and here the potential will have a potential wave, the potentiostat will generate the potential wave, and that is what is applied to the electrode. Okay, and this is potential that you are measuring or applying is the working electrode with respect to the reference electrode, with respect to that. Whatever you measure, the potential difference is with respect to the reference electrode. The wave is, it starts from here, the time 0 goes to the higher value, comes back down, that is what it is. Then again, so this is the potential cyclic voltammetry wave. So how it is done? You start from a particular potential and then start either going in the positive direction or going in the negative direction. That means either you can increase the potential as a function of time, or you can decrease the potential as a function of time, and then reverse it back at a thing. In this case, let us assume we are starting here at this position. So the x-axis is your potential, the y-axis is the current measured. Okay, so more details I will tell you just in a while. So you are changing potential from here as you keep going across a thing. So here, as you can see, so you are slowly, there is no change in the current at all, from minus 0.4 up to about minus 0.1 or so. Then start slowly seeing some increase. What is increasing? Increasing is y-axis, and y-axis is your current. So the current you are increasing, and it goes to a peak value of that, and you are still continuing on your x-axis. X-axis is what? Sweeping the potential. So here you are going from minus 0.4 to minus 0.2, then 0, then plus 0.1, etc., roughly somewhere here. It is not that everywhere you will get here is the peak. Okay, don't take that as a granted. This peak will change one solution to the other, and then the current of that particular side. So whatever is the kind of thing. So what you are doing here, going from negative to positive. So low potential voltage to higher voltage, or going from negative potential to positive potential, going from low negative value to higher negative value to low negative value. All of these are referring to the oxidation processes. So that is what you are looking at here, and so that means the species starts oxidizing maximum amount, and there is maximum current, and then it is decreasing because the species is less amount of species is available at this surface. And remember that you are not stirring the medium when you are measuring this one. You are not stirring. It's a static kind of thing. It is a completely undisturbed solution. Now at this potential you reverse back. That means whatever the potential you have here plus 0.3 start decreasing here. So 0.3 becomes 0.2, becomes 0.1, becomes 0, then minus 0.1, and then goes to minus 0.2, minus 0.3, minus 0.4, and that's how you are going. So now I have taken you a walk path on this. So this is how it's going, and then reversing. You're getting a peak here, and I'll explain these things in a while, what kind of thing. So the potential at this is the oxidation. It is called EPA, sometimes they will also use it as EPA, and that is anodic, and the current here is talked in terms of the EPC. So, this is the cathodic potential and this is the anodic potential, and correspondingly the currents are referred as IPA and IPC. So, this is a cathodic current, anodic current, cathodic potential, anodic potential. So, what is your characteristic potential of your system is called E half. So, E half is a characteristic potential of your thing, EPA plus EPC by 2, that is what it is. Okay. So, other things. So, that is all labeled here, your E half, then EPA, EPC, etc., all of these. What are the kinds of things that you would? So, you have you are doing an electrolysis, electrochemical reaction by changing the potential at the electrode with respect to, you are measuring with respect to the other electrode, working electrode. Okay. So, what are the process of the species reaching the particular electrode surface is, one is the mechanical one. So, this is being not much is there because you don't stir. So, this is where the conventional way of taking the species from the bulk to the towards the electrode. The other one is the electric gradient. Okay. So, that is called the migration current. So, what is electrical gradient? Because your electrode is applied a potential. So, that it means there is an electrical charge on the on the electrode, and this charge has electric field in the neighbor. So, whatever the species will have will be attracted or repelled depending upon the kind of a charge that you have, and that kind of a movement is called the migration. So, this is by the electrical field. Okay. And this also can be basically fixed, and what is that you have is the diffusion, other thing. So, diffusion is, how do you expect a diffusion? Diffusion is expected a species going from a higher concentration region to a lower concentration region. So, you have a bulk where the higher concentration is there, you have a surface where the lower concentration is there, and at the surface you are doing a reaction, that means you are consuming, therefore, the species will start flowing towards the surface, and that is what. So, this is the diffusion current. So, these two can be obviously controlled, the mechanical and migration things, and this is basically the one which you have, and that is what is referred as the Faraday current. I am sure you are aware of all these. Okay. So, that is what you study essentially in these ones. So, working electrode, as shown on the earlier, will have a specific or defined potential, and whatever the potential you are applying to the reference electrode has a definite potential, and you are applying to the working electrode a potential difference between the reference and the working electrode. So, to make it simpler, this is being talked in terms of the working electrode, reference electrode, these are all working, is shown as this, the reference electrode. So, this is RE, and then you have one more which is called the counter electrode. Just in a while I will tell you about the role of each of this. Okay. So, see, so you can see that the reference electrode is the one with respect to you apply the potential to the working electrode, measure the potential change, etc., difference, etc., with that only. Now, the counter electrode is required in this cyclic voltammetry because you are using the micro electrodes, and in order to control the processes which that should not disturb the working electrode kind of thing. For example, you take a electrode, you put it into the solution, then you apply, then start there is some electron transfer occurs either to the species or from the species to the electrode, that means the current is flowing. If you have to make a kind of a circuit, so to complete the circuit you will use the counter electrode. Also you will use the counter electrode because of the electron flow between the working electrode and the counter electrode, that is what basically you measure. and any kind of the kinetics reactions that occur at the counter electrode, that should not inhibit the reactions that are occurring at the working electrode. So, what do you do? Use a huge surface area of the counter electrode. So, large surface area. So, therefore, all the currents are absorbed there. So, it will not affect the kinetics happening at the working electrode. There are some exceptions where we have to keep the counter electrode outside the compartment, but in most of the cases you can keep inside. So, that happens. Some example is given here in the polymerization reaction, etc. So, now you have understood in this cyclic voltammetry, you have a working electrode, you have a reference electrode, you have a counter electrode as well. So, the working electrode to the reference electrode is a potential application, the working electrode to the counter electrode is the current. So, these are the phenomena that. So, if you look at the, so what are the variabilities in this? The solution with the electrolyte. So, use a huge amount of electrolyte in order to bring the conductivity of the species from the bulk to the electrode surface. That is why you use. So, depending upon the kinds of things, this range what is shown here with the color is the one, the range you can use, in that range you can use. Okay. So, for example, here platinum electrode using these kinds of electrolytes. So, you can use from sodium perchlorate, etc., tetrabutyl ammonium perchlorate, a little bit larger range, ammonium hexafluorophosphate, you can use much larger range. So, this range is around 2 to -1, this will be maybe 2 point something to -2 point something, and this can be 3 to +3 to -3 kind of range. So, the working range of the potential will also change depending upon what kind of a electrode that you are using and what kind of a electrolyte you are using, bulk electrolyte you are using, what kind of a electrode you are using also. Another one influence so in platinum, in water at pH 7, the platinum can go within this range, mercury can be useful in this range, carbon can be used, more or less both platinum and mercury ranges in this. So, this platinum means platinum electrode, mercury means mercury electrode, carbon means carbon electrode. So, these are the working electrodes that you are talking about. So, influence of the solvent and the platinum. So, DMF can allow in this range, THF can allow in this range. Dichloromethane cannot allow that much range as the DMF, because the solvent can also get oxidized, can get reduced. Therefore, you have to see carefully that the solvent range. So, solvent should provide or should allow the potential range. Your bulk electrolyte should allow the potential range. Your electrode should also allow the potential range. So, all of these. So, therefore, various kinds of electrodes, various kinds of medium, various kind of electrolytes are being used. Of course, nowadays a lot of electrodes are not just simple pure electrodes like platinum, gold, carbon, etc. They are coated with a lot of things. Some examples I will show you as we move across in this particular kind of a topic when we are looking at. Okay, so we looked at in the couple of slides before the whole scan, and I talked to you about the anodic potential, cathodic potential, anodic current, cathodic current, etc. And I showed you one peak on the top, one peak in the bottom. So, one of them is cathodic, one of them is anodic. Here is the reverse is shown, so no problem, do not worry about that. Okay, because here you are decreasing the potential starting from here. A is the starting point, A is around 0.3 and you are going towards the lower. So, therefore, you are reducing potential or decreasing the potential, not reducing, decreasing the potential. That means it is a reduction process. So, this is your cathodic peak and cathodic peak current, anodic and reverse it, anodic peak current. So, number one, you should see both the peaks, this side and this side. In some cases you will not see, you will know that soon. So, that is one necessity for reversibility. Other thing is the current ratio, the IPC by IPA should be more or less close to 1, as close as 1, and the difference between the EPA and EPC should be 60 by N. So, that is delta E, that means potential difference. So, EPA minus EPC, it does not matter, either way you take it. So, 60 by N. N is number of electrons gone through the process, number of electrons. So, the number of electrons involved in the process, if it is 1, it will be 60 by 1, if it is 2 electrons, it will be 60 by 2, which is 30, and this. So, these three parameters primarily determine whether it is the reaction that you have done, the cyclic voltammetry you have studied, reversible, electrochemical reversible or not reversible. Not reversible means then you may not see both the sides peak, you may see one peak, or you may see both sides, but their EPA by EPA minus EPC difference will not be equivalent to 60 by N. There will be a large gap. So, the potential difference will be large. The third parameter is your current ratios will be very off from 1, may not be very close to that. So, those are some kind of things that you will find. So, that is where we have. I think we will continue to look at probably in the next class about this electrochemical reversibility, then some examples. We will look at both reversibility, irreversibility and examples in the next class. Thank you very much.